Tonight, we are going to sit quietly at the very edge of everything at the moment before anything existed. No stars, no planets, no air to breathe, no ground to stand on, not even the darkness you might imagine, because darkness requires space, and there was none. There was no time ticking forward. There were no laws of physics waiting patiently in some cosmic waiting room. There was nothing, and from that nothing, somehow, everything came. This is perhaps the most quietly astonishing question a human mind can turn toward. How did the universe begin? Not just what happened in those first moments, though we will absolutely get there, but what does it even mean for something to come from nothing? What is nothing, really? And is the question even answerable? So settle in. Let your body grow heavier. Let the questions wash over you, not as puzzles you need to solve tonight, but as open doors leading into a very, very large and beautiful darkness. And let us begin. Before we can tell the story of the Big Bang, it is worth pausing just for a little while, here in the quiet, to think carefully about a single word. A word that seems, at first glance, so simple that it barely needs examining at all. Nothing. In the ordinary world, nothing is easy. An empty drawer is nothing. A silence between two notes in a piece of music. A blank canvas before anyone has touched it. A cup with no tea in it, which in certain households constitutes a minor emergency, but is otherwise just an empty cup. Nothing in everyday life is simply the absence of something specific. The absence of objects in a space, or of sound in a moment, or of meaning in a conversation. The space itself remains. The moment itself remains, the context holds, even when what was inside it is gone. But when physicists and cosmologists use the word nothing to describe what preceded the universe, they mean something far more radical, something that language was genuinely not built to carry. They mean not an empty space, but the absence of space itself. Not a moment of silence, but the absence of time itself. Not a blank canvas, but the absence of any surface on which a canvas could exist, any room in which it could hang, any air around it, any light to illuminate it, the absence of any laws that might govern what happens, because laws require a universe in which to operate, and there was no universe yet. It is worth saying clearly there was no darkness. Darkness is a property of space, the quality of a region of space in which very little light is present. Before the universe existed, there was no region. There was no space to be dark or bright. There was no time during which anything could be said to be happening. There was no during at all. This is the point at which human intuition, having been a reasonably good guide through most of ordinary life, quietly sits down and declines to come further. And that is completely understandable. Our minds evolved to navigate a world of objects and spaces and moments, of things that are here and not there, of events that happen before and after other events. We did not evolve to contemplate the genuine absence of all of that. It is not a failure of imagination. It is, in a strange way, a testament to how unusual the universe's origin actually is. And yet here we are. The universe exists. You exist. These words exist. Reaching you somehow across whatever distance separates the moment they were written from the moment you are receiving them. Something shifted. At some threshold, at the very boundary of comprehensibility. From nothing into something. And what is quietly astonishing, what deserves more than a moment's appreciation, is that science has actually managed to trace what happened next with extraordinary precision. Not to the very first moment, no, that part remains, perhaps permanently, beyond the reach of our current tools, but extraordinarily close to it, closer than we had any right to expect. The story of how we got from nothing to you, lying there in the dark, is one of the most remarkable stories ever assembled, and we have the whole night to tell it. It is also worth pausing before we enter the science to consider why this question matters to us the way it does. There is something almost universal in the human impulse to want to know where things come from. Children ask it instinctively, long before they have the vocabulary for cosmology. Where did I come from? Where did the world come from? Where did everything come from? It seems to be wired into the kind of minds we have, minds that are pattern-seeking, cause-seeking, always tracing the thread of any story backward to try to find where it starts. For most of human history, the answer to these questions was provided by myth and religion stories about gods or forces or primordial substances that gave rise to the world and everything in it. These stories vary enormously across cultures and centuries, but they share a common structure. Something existed before, and from that something, through some act or process, the world as we know it came to be. Science offers a different kind of answer. Not a story of intention or meaning. Science does not address those dimensions of the question, but a story of mechanism, of how rather than why. And the how, it turns out, is staggering in its detail and its strangeness and its beauty. It is a story that, once you have heard it, makes the night sky look different, makes the air you breathe feel different, knowing where its atoms have been. Makes the stars not just beautiful objects in the dark, but kin the ancestors of everything you are made of. So let us enter it carefully, with attention, and with the kind of quiet wonder that a story this large deserves. Let us begin the story at the place where science can actually plant its feet. Approximately 8 billion years ago, a number so large that it is best not to stare at it too directly, the universe as we know it came into being. This event is called the Big Bang. And almost everything that name implies is, in one way or another, a little off, which is something scientists have been politely noting for decades without managing to replace the name with anything better. The phrase has a certain stubborn staying power. It was not, in any conventional sense, a bang. A bang implies an explosion, something violent occurring at a particular point in a pre-existing space, sending matter flying outward in all directions from a center. A bomb going off, a star exploding, some catastrophic event located somewhere, surrounded by a wider emptiness into which the debris expands. The Big Bang was not like that at all. There was no surrounding emptiness. There was no location where it happened. There was no moment before it in which anything was waiting. What we call the Big Bang was not an explosion of matter into space, it was an expansion of space itself. Space, and everything in it, came into being together. Matter and energy and the very fabric of space and time all emerged simultaneously from a state of extraordinary density and heat and began expanding. Every point in space was, at that first moment, essentially touching every other point. The universe was not small the way a tennis ball is small, occupying a modest amount of space with empty space around it. It was small in the sense that space itself was compressed. The distances between things, which is to say, between all things, were essentially zero. And then those distances began to grow. Space itself stretched. And as it stretched, it carried everything within it outward, in all directions, simultaneously. The best analogy, and like all analogies, it is imperfect, but it is the best available, is the surface of a balloon being inflated. Imagine dots drawn on the surface of that balloon. As the balloon expands, every dot moves away from every other dot. No single dot is at the center. No single dot is where the expansion is coming from. From the perspective of any dot, all the others are receding. The expansion is happening everywhere at once. In the surface of the balloon itself, not into anything beyond it. Our universe is like that, except that instead of the two-dimensional surface of a balloon, we are talking about three-dimensional space. And instead of dots, we are talking about galaxies. And instead of air being blown into a rubber sphere, we are talking about the fabric of space-time itself growing, driven by forces we are only beginning to understand. This is the first place in the story where the ordinary logic of things quietly fails us, and it will not be the last. Part of what makes cosmology, the study of the universe as a whole, so genuinely fascinating is that it requires us to set aside, gently and repeatedly, the assumptions that feel most natural and follow the evidence into territory where our intuitions cannot easily go. This is the first place in the story where the ordinary logic of things quietly fails us. And it will not be the last. Part of what makes cosmology, the study of the universe as a whole, so genuinely fascinating is that it requires us to set aside, gently and repeatedly, the assumptions that feel most natural and follow the evidence into territory where our not easily go. That is, in a quiet way, part of what makes it worth exploring at bedtime. There is something restful about the discovery that the universe does not feel bound by what seems reasonable. Before we press on into the first seconds, it is worth a brief and gentle detour into how we know any of this at all. It is a fair question. The Big Bang happened 13.8 billion years ago. No human being was there. No instrument of any kind was there. The first stars lit up hundreds of millions of years later. The Earth formed billions of years after that. Homo sapiens appeared perhaps 250,000 years ago, and the first telescopes were built less than 500 years ago. How, from this tiny vantage point in time and space, have we managed to piece together the history of the entire universe? The answer is light. Light in physics is not merely something that helps us see. It is information, traveling at the fastest speed anything in the universe can move. When you look at the sun, you are seeing what the sun looked like 8 minutes ago. That is how long its light took to travel to your eyes. When you look at the nearest star beyond the sun, you are seeing it as it was 4 years ago. When you look at the Andromeda galaxy on a clear night, a faint smear of light visible to the naked eye, you are seeing it as it was 2.5 million years ago. The further away something is, the further back in time we are seeing it. And because the universe is so vast, we can look back enormous distances in time simply by looking at things that are far enough away. The most distant galaxies we have observed with instruments like the James Webb Space Telescope are so far away that their light has been traveling for more than 13 billion years. We are seeing them as they were when the universe was less than 1 billion years old. This is not an approximation. It is a direct consequence of the finite speed of light, which is one of the most precisely measured quantities in all of science, approximately 299,792 kilometers per second. Light speed is the same everywhere in the universe, for every observer, regardless of how fast they are moving. This constancy, one of the foundational results of Einstein's special theory of relativity, is what makes the universe's history readable in its light. And then there is the cosmic microwave background, which we will encounter shortly, and the abundances of elements, and the way galaxies cluster and filament across space. Each of these is a different kind of record, a different page in the cosmic archive, readable with instruments of sufficient sensitivity. We have been very lucky as a species to develop both the curiosity and the mathematical tools needed to read these pages. And we are still reading. Now, the very first moments. We cannot directly observe the universe in its absolute first instant. The mathematics we use to describe the physics of space and time, Einstein's general theory of relativity, breaks down completely when we try to apply it to the conditions that would have existed at the very beginning. Temperature and density become, in the equations, infinite, and infinite, in this context, is not a description of something very large. It is a signal that the theory has reached its own boundary, that something in our understanding is missing. Something important remains to be discovered. This breakdown is not a failure of the theory in any other respect. General relativity is one of the most precisely tested and confirmed theories in all of science. It correctly predicts the behavior of gravity in nearly every situation we can test, but at the singularity, the name given to that first moment of infinite density, it stops. It reaches a wall. And what lies on the other side of that wall is, for now, one of the great open questions in physics. But here is the remarkable thing. We do not need to reach all the way back to that first instant to tell a fascinating and scientifically grounded story. We can begin a tiny, tiny fraction of a second later. A fraction of a second so small that no human vocabulary of smallness really does it justice, something on the order of 1/10,000,000th of a trillionth of a trillionth of a trillionth of a second after the beginning. And at that point, even that young, even that close to the very edge of everything, we can say something scientifically meaningful about what the universe was like. And what it was like was this: extraordinarily hot, extraordinarily dense, and extraordinarily strange by the standards of anything we encounter in everyday life. The temperatures in those first moments were so extreme, we are talking about numbers in the trillions of degrees. And beyond that, the very concept of ordinary matter had no meaning. The things we think of as the fundamental building blocks of the world, protons, neutrons, the atoms they form, could not exist at those temperatures. The conditions were so energetic that matter and energy blurred together, interchanging freely. Einstein's famous equation, the one about energy equaling mass multiplied by the speed of light squared, was not a curiosity in those first moments. It was a description of reality in real time. Energy was becoming matter, and matter was dissolving back into energy, constantly in all directions at once. The universe in those first moments was a searing, churning, almost indescribably energetic soup. There were quarks, the tiny particles that in cooler and quieter conditions clumped together to form protons and neutrons. There were electrons zipping through the plasma at nearly the speed of light. There were photons, particles of light in enormous abundance, colliding with everything, unable more than the tiniest distance before hitting something else. There were neutrinos, ghostly particles that barely interact with anything, but were present in staggering numbers. There were the particles that carry the fundamental forces, the gluons that hold quarks together, the bosons associated with the weak nuclear force. Everything was present. Everything was interacting. Everything was in furious, continuous, spectacular motion. If you had been able to stand there, which you could not, for reasons that go rather beyond the obvious practical difficulties, you would not have seen anything. Not because it was dark. There was an almost unimaginable flood of light. But the light had nowhere to go. The plasma was so dense that a photon could travel no distance at all before being absorbed or scattered by the particles surrounding it. The universe was opaque, brilliant, searing, and completely opaque. And then, very slowly by cosmic standards, the universe began to cool. There is something else worth mentioning about those first extraordinary moments, something that gives the story an additional layer of quiet depth. Today, nature operates through four fundamental forces. Gravity, which governs the large-scale structure of the universe, the orbits of planets, the collapse of stars, the clustering of galaxies. Electromagnetism, which governs the interaction of charged particles, the behavior of light, the chemistry of atoms and molecules. The strong nuclear force, which holds the nuclei of atoms together against the electromagnetic repulsion between their protons. And the weak nuclear force, which governs certain kinds of radioactive decay and plays a critical role in how stars produce energy. These four forces appear, today, to be quite distinct. They operate over different ranges with different strengths through different carrier particles. A physicist working with electromagnetism and a physicist working with gravity are in many respects working with very different tools. But there are strong theoretical reasons and some observational hints that in the extreme heat of the earliest universe, these forces were not distinct at all. They were unified. At sufficiently high temperatures and energies, the differences between the forces dissolve, and what we perceive as four separate phenomena merge into far fewer, perhaps into one. The moment at which even gravity unified with the other forces is called the Planck epoch, and it corresponds to temperatures and energy scales so extreme that our current physics has nothing to say about it. This is precisely where the mathematics breaks down, where the theory produces infinities and loses its ability to make predictions. It is the edge of the map, the place beyond which our tools do not work. And it is one of the deepest motivations for research in theoretical physics today to develop a framework that can handle both quantum mechanics and gravity simultaneously, because that framework would allow us to describe what was happening in those first unimaginably brief moments. Various candidates exist. String theory is perhaps the most widely discussed, though it remains unproven. Loop quantum gravity is another. There are others still, each making different predictions about the Planck scale structure of space and time. None of them has yet been confirmed by experiment. None may be for some time, or perhaps ever, given the enormous energies involved. But as the universe cooled from those extreme early conditions, the forces separated from one another, one by one, in a process physicists call symmetry breaking. Gravity separated first. Then the strong nuclear force. Then the electromagnetic and weak forces separated from each other. In an event that we believe occurred at a temperature of about 1 quadrillion degrees of temperature that our most powerful particle accelerators have very recently and very briefly approached. With each separation, each new distinction between forces, the universe became more structured, more varied, more capable of producing complex things. It is as though the universe was revealing itself in stages, each phase of cooling uncovering new possibilities that the heat of earlier moments had kept compressed and hidden. The rich variety of particles and forces and atoms and molecules and stars and galaxies and living things that we see today was, in the first moment, all bundled together in a single undifferentiated state of extraordinary simplicity and heat. We are, in a sense, the product of an extraordinarily long cooling process. Cooling, in the universe's early history, is not simply a matter of temperature dropping. It is a story of structure emerging. As the universe expanded and the space between its particles grew, the frantic, energetic collisions that had been preventing anything from holding together became rarer. The universe, little by little, became a slightly calmer place. And as it calmed, things that had been impossible in the heat started to become possible. The first major threshold came at around 1/10,000th of a second after the Big Bang. By that point, the universe had cooled enough, if we can use that word for temperatures still well into the trillions of degrees, for quarks to stop flying freely and begin binding together. 3 quarks, pulled toward each other by the strong nuclear force, formed protons. 3 quarks in a slightly different configuration formed neutrons. These tiny, dense particles, far smaller than atoms, stabilized in those first fractions of a second. They are still with us today. The proton at the center of every hydrogen atom in your body was formed in that brief window of time, in conditions so extreme that no laboratory on Earth has ever come close to recreating them. For a brief period there were also antiparticles, an antiproton for every proton, an antineutron for every neutron. Matter and antimatter, produced in almost exactly equal numbers by the energetic conditions of the early universe. And when matter and antimatter meet, they annihilate each other, vanishing in a flash of pure energy. Which raises a question that is worth pausing on, because it is one of the most important questions in cosmology. We exist. Which means matter won. Which means there was a slight excess of matter over antimatter, roughly 1 extra particle of matter for every billion matter-antimatter pairs. Why? What caused this tiny asymmetry? The honest answer is that we do not fully know. There are theories, some of them quite mathematically elegant, but none of them has been confirmed to the degree that would settle the question. What we know is that without that slight imbalance, without that fractional excess of matter over antimatter, every particle produced in the Big Bang would have been annihilated. the universe would have consisted of nothing but light. No stars, no galaxies, no planets, no curious minds wondering how it all began. That quiet, fractional asymmetry is, in a very real sense, the reason you exist. About 3 minutes after the Big Bang, and it is worth pausing every time we say something like 3 minutes after the Big Bang, because that sentence contains multitudes. The universe had cooled enough for protons and neutrons to begin sticking to each other. Not into full atoms, electrons were still far too energetic, and the temperatures far too high for that. But the nuclei, the dense central cores of atoms, began to form. This process is called Big Bang nucleosynthesis, which is a phrase that sounds far more complicated than what it is describing. It simply means the formation of atomic nuclei in the first minutes after the Big Bang. And what it produced was predominantly hydrogen. Hydrogen is the simplest element, a single proton, sitting on its own, needing nothing else to be itself. In the very hot, very dense early universe, most protons never acquired a neutron companion. They became, and remained, hydrogen nuclei. Some protons and neutrons did combine. 2 protons and 2 neutrons, bound tightly together by the strong nuclear force, form the nucleus of helium. And in the early universe, roughly 25% of all the normal matter that existed became helium-4 in this way. About 1 in 12 protons ended up in a helium nucleus, while the rest remained as lone hydrogen nuclei. There were also tiny amounts of other light elements, trace quantities of helium-3, deuterium, which is a form of hydrogen with 1 neutron added, and the lightest form of lithium. These were produced in very small quantities, and they are still there today, embedded in the oldest and least altered clouds of gas in the universe, providing a kind of chemical fingerprint of what the Big Bang produced. When astronomers measure the abundance of these elements in ancient gas clouds and compare them to the predictions of Big Bang nucleosynthesis, the agreement is remarkably close. It is one of the strongest pieces of evidence we have that our understanding of the early universe is correct. But beyond those light elements, hydrogen, helium, a whisper of lithium, the early universe had nothing else. No carbon, no oxygen, no iron, no calcium, no silicon, no nitrogen. Every element heavier than lithium that exists anywhere in the universe today was made later, inside stars, and we will come to that in due course. This is worth sitting with for a moment because it is genuinely extraordinary. Every periodic table you have ever seen, that elegant grid of elements, from hydrogen at the top, left through uranium and beyond, represents over 100 distinct kinds of atoms. Of those, the Big Bang produced meaningful quantities of exactly 3: hydrogen, helium, and a small trace of lithium. The other 100+ elements came later, built one by one in the nuclear furnaces of stars. The periodic table, in that sense, is not just a chart of chemistry. It is a map of cosmic history. The heavier an element is, the later in the story it was made, and the more dramatic the stellar processes required to make it. Iron, for instance, sits roughly in the middle of the periodic table. It is the endpoint of nuclear fusion in the core of a massive star, the element at which fusion becomes energetically unfavorable, and which, when it accumulates in sufficient quantities, triggers the catastrophic collapse that ends the star's life. The gold in a piece of jewelry, or the uranium in a nuclear reactor, is heavier than iron and was not made by ordinary stellar fusion at all. It required conditions found only in the collision of two neutron stars, or in the extreme shock waves of a supernova's final moments. Every gold atom that has ever existed was made in an event of almost incomprehensible violence, in a universe far younger than it is today. The early universe, with its three elements, was not yet capable of any of this. It was, in the grand scheme of chemistry, extraordinarily simple. But it held within its hydrogen and helium all the potential that would, over billions of years, unfold into everything that came after. For now, the universe settled into what would be a very long, very hot, very opaque period. Hundreds of thousands of years of a plasma of nuclei and electrons and photons, all tangled together in an expanding, slowly cooling sea. 380,000 years after the Big Bang. Let us sit with that number for a moment. 380,000 years. This is longer than the entire span of modern human prehistory, longer than the entire time our species has existed on Earth. And in the life of the universe, it is barely an opening breath. For all of those thousands of years, the universe was opaque. Light could not travel freely. Every photon that was emitted was almost immediately scattered, bounced off an electron, redirected, scattered again. The universe was a kind of luminous fog, filled with energy, filled with light, but impossible to see through. It was bright, in a sense, but not transparent. A photon produced at one end of the observable universe could not possibly reach the other end. It would travel a tiny distance and then careen into a free electron and be sent in a new direction. And then, at around 380,000 years after the Big Bang, something happened that changed everything. The universe had cooled to about 3,000 degrees, still extraordinarily hot by any earthly standard, but cool enough for something that had never before been possible. Electrons, which had until this point been free-ranging and energetic, began to settle. They slowed enough that the electric attraction between them and the positively charged atomic nuclei around them could take hold. They dropped into stable orbits. They combined with nuclei to form the first complete neutral atoms. In physics, this moment is called recombination. The name is slightly misleading. As we touched on earlier, it implies a reunion of things that had been together before, when in fact electrons and nuclei had never been combined prior to this moment. They had always been separate. This was their first meeting, not a reunion. History has decided not to revisit this naming decision, and we move on. When neutral atoms formed, the free electrons that had been scattering all the photons disappeared. They were captured. And with the scatterers gone, light was suddenly, for the first time in cosmic history, free to travel. Photons that had previously been trapped in the thick plasma could now move in straight lines across the universe, covering enormous distances without interruption. The universe became transparent in what was, cosmically speaking, a remarkably short time. The fog lifted, and as it did, a flash of light was released aglow, filling all of space. The thermal radiation of a universe at 3,000 degrees suddenly freed to travel. That light is still traveling today. It has been moving through space for nearly 13.8 billion years. As the universe expanded around it, the wavelength of that ancient light was shifted from the warm glow of visible light into the much longer wavelengths of microwave radiation. And so today it fills the entire sky in every direction as a faint and extraordinarily uniform bath of microwave energy. It has a temperature of just under 2.7 degrees above absolute zero. It is called the cosmic microwave background radiation, and it is, without any exaggeration, one of the most important things ever detected. When astronomers point sensitive instruments at the sky and measure this ancient glow, they are not looking at something nearby. They are looking at the surface of last scattering the layer of the early universe from which those photons were released, 380. 0 years after the Big Bang. They are, in the most literal sense available, looking back almost to the beginning. They are seeing the oldest light in the universe. But it is not the existence of this glow that is most remarkable. It is what is within it. The cosmic microwave background is not perfectly uniform. It is almost perfectly uniform. The variations in temperature across the sky are tiny, on the order of 1 part in 100,000. But they are there. And they are not random noise. They are a structured pattern, imprinted on the universe by the physics of that first 380,000 years, the slight variations in density that existed in the early universe, the acoustic oscillations of that primordial plasma, the gravitational influences of whatever seeds of structure were present from the very beginning. These patterns are, in effect, a photograph of the universe at 380 years old. And embedded within those patterns are the seeds of everything that came afterward, every galaxy, every cluster of galaxies, every vast structure that would take billions of years to grow. When we look at the cosmic microwave background, we are looking at the blueprints of the cosmos written in light that has been traveling since before a single star existed. Astronomers have mapped this ancient glow in extraordinary detail, using satellites like COBE, MAP, and the Planck satellite. The precision of these measurements and the extraordinary agreement between what is observed and what the theory of the Big Bang predicts is one of the things that gives cosmologists genuine confidence that they are on the right track. After recombination, the universe entered a period that is sometimes called the Cosmic Dark Ages. It is a fitting name. The light that had been freed at recombination was real, it was there, filling space. But there were no stars yet, no galaxies, no compact sources of light of any kind. The photons released at recombination had already spread out and stretched into longer and longer wavelengths, and the universe contained nothing but vast, thin, slowly expanding clouds of hydrogen and helium gas drifting in an expanding darkness. Try to picture it, or rather, try to let the picture form without forcing it. A universe that extends in all directions without limit. A cosmos filled with gas, not the thick, warm air of a room, but gas of extraordinary thinness, billions of times less than the best vacuum that can be created in any laboratory on Earth. And through this thin gas, no light, no warmth, no radiation of any significance, just the slow, steady expansion of space, carrying everything within it apart from everything else. The gas growing thinner, the universe growing dark, and, for what would turn out to be somewhere between 150 million and 800 million years, nothing else. This is a vast span of time. If the entire history of the universe were compressed into a single year, the cosmic dark ages would occupy roughly the first 1 to 2 weeks of January. During those weeks, not a single star would shine. Not a single photon from a luminous object would cross the void. The universe would be quiet in a way that has no equivalent anywhere in the world we know. And yet, within this silence, something was happening that would change everything. Gravity was working. Gravity is, in a way, the most patient force in nature. It does not require extreme conditions to operate. It does not need high temperatures or high densities. It works at every scale, across every distance, and it never stops. And in the dark universe of those early hundreds of millions of years, gravity was slowly, steadily doing what it always does, pulling things toward each other. The gas was not perfectly uniform. There were slight variations in density regions where the gas was fractionally denser than average and regions where it was fractionally thinner. These variations were tiny, but they were there, baked into the structure of the universe from the patterns we saw in the cosmic microwave background. And wherever the gas was slightly denser, gravity was very slightly stronger. So the slightly denser regions pulled in gas from their surroundings. And as they grew denser, they pulled harder. And as they pulled harder, more gas flowed in. And the process built on itself, slowly but continuously, across millions of years. There is something deeply calming about this image, if you let it settle. The universe, in the dark, quietly building. No drama, no catastrophe, just the soft, constant accumulation of gas drawn toward gas over millions of years in silence. Nothing to see, nothing to hear, just the invisible architecture of the future, assembling itself in the dark. And here is where dark matter plays a role that is worth understanding. Because it is not a minor supporting character in this story. It is, in many ways, the scaffolding on which everything else was built. Dark matter does not interact with light. It does not emit it, absorb it, or reflect it. If you shone a flashlight at a cloud of dark matter, the beam would pass straight through with no effect whatsoever. This is why dark matter is dark, in the physical sense, not because it is in shadow, but because it is genuinely invisible to electromagnetic radiation of any wavelength. But dark matter does interact gravitationally. It has mass, and mass curves space, and curved space exerts a gravitational pull. And because dark matter was present in enormous quantities in the early universe, making up roughly 5 times as much mass as ordinary matter, its gravitational influence was enormous. It was dark matter, clustering under its own gravity in the Dark Ages, that first built the large-scale structure of the universe. The vast filaments and sheets and clusters of matter that today trace the 3-dimensional architecture of the cosmos, what is sometimes called the cosmic web, were seeded by the gravitational clustering of dark matter in those first hundreds of millions of years. Ordinary matter, hydrogen and helium gas, simply fell into the gravitational wells that dark matter had already prepared. The dark matter formed the structure, the gas followed. And where the gas was densest, in the deep center of those dark matter concentrations, the temperature and pressure climbed high enough for fusion to ignite. The thin wisps of gas in the denser regions began to gather into larger clouds. Those clouds grew. They cooled as they did, releasing heat as they compressed, but also stretching and thinning in the outer parts where gas was being drawn inward. And inside the densest, most collapsed parts of these gathering clouds, temperatures began to rise again. Pressure built. Density built. The gas at the centers of these forming clouds grew hotter and hotter, compressed under the weight of all the gas above it, pressing in from all sides. And eventually, in the cores of the densest of these clouds, something happened that had never happened before in the history of the universe. The temperature climbed high enough, around 10 million degrees, for hydrogen nuclei to begin fusing. Nuclear fusion. The process by which the cores of light nuclei are forced close enough together that they can merge into heavier nuclei, releasing an enormous amount of energy in the process. The first star lit up. This moment, cosmic dawn, as it is sometimes called, is one of the most significant thresholds in the entire history of the universe. Hundreds of millions of years of darkness, and then, in some cloud of collapsing gas in some part of the early cosmos, a new light flickered into being. A star. And then another. And then more, as other clouds crossed the same threshold, as the same process of gravitational collapse and heating and ignition played out across the universe. Within a few 100 million years of the Dark Ages beginning to end, the cosmos was lit with the light of those first stars. What were these first stars like? They were not like the stars we see when we look at the night sky today. They were almost certainly far more massive, some of them possibly hundreds of times the mass of our own sun, perhaps even approaching 1,000 times as massive. They were made of essentially pure hydrogen and helium, because those were the only elements that existed in the universe at the time. And their extreme mass meant that the pressure and temperature at their cores were extraordinarily far more extreme than in a smaller, gentler star like our sun. They burned ferociously. They consumed their hydrogen fuel at a rate so rapid that their lifespans were measured not in billions of years, as the sun's will be, but in millions. Some of the most massive may have burned for only a few million years before exhausting their fuel entirely. And when they did exhaust their fuel, they died in the most dramatic way available to physics. A star lives in a kind of balance. The gravity of all its mass pulls inward, trying to collapse the star. The energy produced by nuclear fusion in the core pushes outward, a constant pressure that keeps the star from collapsing. As long as fusion is producing energy, the balance holds. But when the fuel is exhausted, the outward pressure fails. And then gravity wins, very suddenly. The core collapses. In the most massive stars, this collapse happens in a fraction of a second, a catastrophic infall that is so rapid and so violent that it triggers a rebound, an explosive shock wave that blasts the outer layers of the star outward in all directions. This is a supernova. One of the most energetic events in the universe, releasing in moments more energy than our sun will produce over 10 billion years. But what came out of that explosion was not nothing. What came out was new. Because inside that dying star, in the extreme temperatures of its final stages, something remarkable had been happening. The hydrogen and helium in the core had been fusing into heavier elements. Helium fused into carbon and oxygen. Carbon fused into neon and magnesium. Heavier and heavier elements were produced, layer by layer, in the final stages of the star's life, as it burned through its reserves and tried to find new fuels. Iron formed last. And iron is where fusion stops. It takes more energy to fuse iron than the process releases, so when the core of a massive star becomes iron, fusion ceases and collapse is inevitable. And in the supernova that follows, the energies are so extreme that elements heavier than iron can form briefly in the shock wave. Gold, silver, uranium. These are elements that can only be forged in the extraordinary conditions of a dying star's final moments, or in the merger of two neutron stars, the collapsed remnants of stellar cores, which are among the most violent and energetic events in the universe. All of this material, this library of newly created elements, the first heavy atoms in the history of the universe, is blasted outward by the supernova explosion.